conference. We have, can you hear me now? Yeah. So in this session, we have Umesh Vazirani with us from University of Berkeley. Umesh is Robert Strauch Professor of Electrical Engineering and Computer Science at Berkeley, and he's the director of the Quantum Computation Laboratory. And Umesh is one of the pioneers of this field of quantum computation and quantum complexity theory. And his work in algorithms and quantum computation are deeply influential in theoretical computer science. It's a great pleasure to have Umesh. He has won many honors and awards. I should mention that he's a fellow of ACM, the Association for Computing Machinery, which is a very important thing for us. And then he, I should say last year he got the Fulkerson Prize for his work on approximation ratios. And well, it's a great pleasure to have Umesh here. He's going to tell us about something extremely interesting to all of us. There is a massive online course.
Thanks, thank you, Jam. Yeah, it's an honor to be here, and let me tell you a little bit about this is a topic that I feel particularly excited about. It's I'm sure you all know about Gutenberg, who invented the printing press back in the 15th century, and oh, nice. This was considered so significant that I even wrote it twice. So why was it such a significant invention? Well, because this is this is one of the major discoveries that historians point to when they say, what was the pivotal discovery that allowed Europe to emerge from the Dark Ages and into the Renaissance? And so, well, you can consider why should this be the case? Well, before the printing press, people used handwritten manuscripts, which were expensive, scarce, laborious, so they were available to only a few. And actually, just before Gutenberg invented his printing press, there were rudimentary printing presses that existed. They were based on cloth printing, so this was so-called block printing. But it was very low quality, not so efficient. You really could not take a book and print it in this way. Mostly pictures with a few words. Okay, so what did Gutenberg do? Well, he invented the printing press around 1440, and it took the world by storm, or at least Europe by storm. So by the end of that century, there were thousands of printing shops. About 20 million books had been printed. And if you look at the speed at which books could be printed, here's the comparison. Basically, 3,600 pages per day on a printing press that he invented versus 2 to 3 hand copying and 40 in this hand printing method. So it was really a big deal. Okay, so let's move into the future and into the present, I guess. So this is one of my favorite cartoons. It's by Bernard Chazelle at Princeton. Well, of course, this is, he talked, in his cartoon, it's a conference on the future of computing, but you could, of course, make it the future of education. And, okay, so where are we with respect to education? Okay, so about a year and a half ago, there was something very significant that happened. So Sebastian Thurn and Peter Norvig, Sebastian Thurn, who was on leave from Stanford at Google X, and Peter Norvig decided to offer an online course on artificial intelligence. By mistake, Well, we think it's by mistake. Sebastian posted on a blog that students who finish the course with a sufficiently high grade would get a certificate from Stanford. 160,000 students signed up. They had to deal with the mess. They've eventually figured out that Stanford, of course, would not issue a certificate, but there would be instead there would be a certificate. You know how you can name a set by its complement? So the certificate said, "This is not a certificate from Stanford. This is not. Stanford does not take any responsibility." And it said it so many times that you saw Stanford everywhere on the certificate. 2 weeks later, Andrew Ng and Daphne Kohler from Stanford went online with their own machine learning course, and 100,000 students signed up. Now, signing up doesn't mean completion, right? So there are factors of 2 that happen. So you have n number of people who sign up, n over 2 watch the first video, n over 4 submit the first homework, n over 8 are still active halfway through the course, n over 16 sort of finish and get a certificate, or n over 10. It is roughly order of magnitude. So the completion rate is 8 to 10%. Okay, but that's to be expected since since signing up is such a light process. There's no commitment of anything at all. It takes 2 minutes to sign up, 5 minutes if you want to come up with an interesting user ID name. Okay, and by now, we have at least 3 different ventures: Coursera and Udacity and edX. edX is a non-profit; the other 2 are for-profit companies. edX is a consortium with MIT, Harvard, and Berkeley. Okay. Now, there's a lot of excitement about this online education. There's also a lot of trepidation. You see university administrators sort of, you see them sort of shivering by the deep end of the pool, sort of trying to decide whether they should plunge in or not. And there's a saying on Wall Street which sort of describes how this goes. So the saying on Wall Street goes, "Don't panic. But if you do, be the first." Okay, and so I think that one could even say that this is the main reason that this is taking off so quickly, because All right, so now how should we think about this whole phenomenon? Okay, there are those who are extremely excited about this. Okay, so they would say, this is going to be a revolution in education comparable to the printing press in the 15th century. Why is that? Because it's going to flatten the world like, Friedman did not know nothing. When he was saying the world is flat, it was sort of for not very deep reasons. But here, you could say the world is going to be flat. Because knowledge really matters. And suddenly you're going to have everybody, just anybody, anywhere in the world will have access to the highest quality education. Right? What an amazing thought. This is really an extraordinary thing if you think about it. Okay. Okay, so, and then there's this fear. The fear is that once this happens, what role are universities going to play? So maybe most universities would have to close. And some universities would stay alive, maybe those that are actually preparing these courses, maybe those that are where you have research faculty who are doing interesting research, but maybe 90% of universities would have to close.
I see that you listed among the pros.
I'm sorry?
I see that you listed among the pros.
Oh, did I list it among the pros? Yeah, sorry. Sorry, I didn't, I wasn't thinking. I just went down the irrational exuberance. Maybe that's what I should have labeled the left column. Then there are the people who say, look, oops, what did I do? You know, we've had things like this happen every generation. You know, there are textbooks, there are video lectures, you know, TV. Do you realize that when TV was first introduced, it was not about watching your latest soap opera. It was supposed to be about education. Right? It was supposed to be the case that everybody would now have access to high-quality education. Nothing, it didn't go anywhere. Then, of course, there were lecture videos, you know, DVDs, online lectures, YouTube lectures. Didn't have an effect, right? It had some effect, but you know, and there are universities which do this. They're online universities, but they're off the radar. You know, if you're at a serious institution, they are sort of, you know, they're not on the radar. Whereas this, you know, this involves the best, you know, institutions. It's really a different caliber of courses. Then there are those who say, well, you know, just wait. You know, people in faculty are pouring in their own time gratis to do this, but, you know, this is not going to go on forever. And so this is going to come to an end. And then there are those who say, well, you know, online education, you completely misunderstand education. Education is about personal contact. It's about inspiring the students. It's about giving them feedback. It's about seeing how they're doing. It's about understanding them and giving them feedback. You know, seeing what their blind spots are. That's what education's about. This is, you know, this is really, you know, it's, you know, it's sort of a weak imitation of education. And so, you know, what these developments do, you know, highlight are these questions. You know, what is education? Is it the teaching of facts? Is it the teaching of concepts? Is it individual feedback? Is it inspiration? You know, how should we think about it? Well, you know, what is really important to education? So, you know, I've been thinking about education for a long time. I'll tell you why. There was an incident when I was in second grade which started me thinking about this. Okay, so you know, I'll make these two observations about education. These were sort of inspired by personal experience, but you know, this, if I were to think about what I understand about education, which is admittedly not that much, but there are only two things I understand, and I'll tell you what those are, and of course, you know, there's probably a lot more to it, but so when I was in second grade, I was at the, you know, my mother came to the parent-teacher meeting in my class, and she was really very perturbed, very surprised, you know, because I was plumb at the bottom of the class. And so she talked to the teachers, and the teacher said, well, you know, he comes into class every day and he doesn't know homework. You know, so they asked me about it. They called me over, asked me about it, and my mother said, well, you know, he comes home every day. I ask him, is there any homework to do? And he says no. And then he goes downstairs to play with his friends. So so they asked me, and I was completely oblivious to all this. You know, this notion that somebody would assign you homework and you're supposed to do it at home, it struck me as so bizarre, I didn't even consider it as a possibility. So, and moreover, I had a bad memory, so of course, you know, anything that was said in class, you know, do this, do that, you know, I didn't remember any of that, of course. So what they did was, my mother got me a diary, the teacher would write the homework every day, my mother would ask to look at it, and you know, that's how I proceeded. At the next parent-teacher meeting, I was, you know, sort of the parents were all sort of, there was a buzz because here was this dullard who was at the bottom of the class, and now he was near the top of the class within a few months. Okay. So what, you know, why was this so important to me? You know, I don't know if it was important to me right away, but certainly within a few years after that, I certainly by the time I was in 5th grade, I was really aware of this. I was aware of the fact that there might be, you know, that you know, it seemed to me everybody had something that stops them, you know, some barrier to learning, right? And I just happened to have somebody who sort of intervened, looked into it, right? And so this, to me, was a very important aspect of education. You know, this, and since then, you know, I've noticed this is true at every level, at every level. You know, it's true at the you know, it's, of course, it was true in high school. It was true at the undergraduate level when I teach undergraduates. It's true with PhD students. You know, often when you're a PhD advisor, you'd imagine the most important thing you have to do is teach them about research. It's not true. You know, often the things that keep them from achieving their potential is something very different. You've got to figure that out, right? It's true at every level of, you know, okay. So now if we think of that as an important part of education, surely online education is a non-starter. Okay, so that's the one thing. The second thing is, well, this was another observation that I made, which is, at least as far as I was concerned, and I thought that I was unusual in the sense that, and maybe I was extreme in the sense, but okay, so that, you know, that I'd go for a long time without understanding anything. And then suddenly I'd understand that subject. You know, so people, as far as I could tell, people sort of understand, and their understanding keeps increasing. For me, it was sort of 0-1. But then I realized it's not so unusual, that many people are like this. You know, that okay, so here's the sense in which you can make this observation. You know, so if somebody doesn't understand your lecture, you might imagine they didn't understand it because it's too fast. You went too fast. Okay? And that's often true. But I think it's equally often true that they don't understand it because you went too slow. Okay, let me give you a mental image for this. So let's say that you know, you're looking at a photograph, you know, you're downloading a photograph, it's coming in over the internet. You have a very slow connection. So it's coming in very, very slowly, pixel at a time. The chances are you won't even recognize the photograph. It's so slow, you have no idea what's going on. Whereas if you see the whole picture, it's very easy. Even if there's a sketch, it's easy, right? But a slow, methodical, you know, so being slow and methodical might be a good thing, but in some cases, but it's so boring, and people just, you know, turn off. Okay, so again, it seems, you know, this is another principle, which is that you want to make sure that you're presenting concepts sufficiently fast that people can actually see them. They can see the picture. But in order to do that, you also have to make them sufficiently clean and clear so that you can sustain this rapid pace. Okay, so teaching well is this two-step process, you know, where you want to simplify so much that you can present the material fast enough that you can provide a picture. Okay, now last year, you know, soon after this this course in the fall, you know, the two courses that's, you know, that I spoke about. In the spring, I was tempted to offer my quantum mechanics and quantum computation course online. I was teaching it in the spring, and what I was going to do was record my lectures and put them online, edit them, and so on. And once I started doing that, I realized that it wouldn't work that way. It just wasn't going to work out right. And so I decided over the summer I'd actually offer the course. So here's what the course was. I offered it on Coursera, which was one of these. It was an introduction to, it was an undergrad course. It was an introduction to quantum mechanics and quantum computation. Okay. So here was the, so why did I want to offer this course despite all the things that I said? You would have thought that with the observations I made, an online course would be the last thing I would ever want to do. So there were three reasons. So the first reason was, I thought that, there are very few institutions in the world which offer an undergrad course in quantum computation. And I thought this would be a very good thing to do, to make it accessible, because I thought that there would be some demand for it. Maybe a few hundred students would sign up, but a few hundred, is the size of the field. So, that's sort of a good thing to do. I teach 35 students per semester at Berkeley. Maybe a few hundred serious students was worth reaching out to. The second reason was this was a novel introduction to quantum mechanics. Okay, it was a simple introduction to quantum mechanics. And it was an introduction to quantum mechanics inspired from quantum computation and quantum information. So there's an approach to teaching quantum mechanics that comes from this viewpoint. And in fact, in the early days of quantum computation in the 90s, many of us thought that this is what we should do, that this is what should happen. Unfortunately, nobody, no physics department is going to say to a computer science professor, you tell us how to teach quantum mechanics. It's just not going to happen. So I thought, well, why not just go directly to the students? Why not put it out there? So that was my second reason. There was a third and fourth reason, maybe a third reason, which had to do with these aspects. So it seemed to me paradoxically that maybe online education did have something to say about these features. But I didn't know, and it was an experiment. I was excited to try and see what would happen. So that's what it was for me. It was an experiment. Okay, so let me tell you a little bit about this course, a little bit of background about quantum computation, about why this kind of introduction to quantum mechanics I think is a very interesting thing, and then I'll tell you what I learned about the course. Okay, so by the way, right now I'm using a laptop to project the talk, but when I did the course, I was actually using a tablet. So the course would start with I'd have some slides which were PowerPoint, and then I'd write on them. Okay, these are not slides from the course. These are slides from there was one lecture I gave in the algorithms course at Berkeley on quantum computation, where I used the tablet. So, okay, so it gives you a sense of what you do with a tablet, except that when I do a course, in the actual videos on the course, there's much more freehand writing. Okay, all right. So a little bit about. Maybe you can't see, but maybe I'll outline it. So the basic entity in quantum computation is called a qubit. Quantum bit. Okay, so here's a way to think about it. So let's say you're a hydrogen atom. Its electron can either be in the ground state or in an excited state. So think of this as encoding whether the bit is 0 or 1, ground excited. So let's represent ground as 0, 1 as excited state. And now, one of the fundamental axioms of quantum mechanics is that the quantum system doesn't make up its mind which of these distinct states it's in. So it's in a superposition of 0 and 1. So it's in the ground state with some amplitude, and in the excited state with some amplitude. But these are not probabilities. These are complex numbers. And these are normalized so that the sum of the squares is 1. And now if you look at the electron, it quickly makes up its mind whether it's in the ground or excited state. It's in the ground state with probability alpha magnitude squared, excited with probability beta magnitude squared. And then no matter, whatever you see is what the new state is. So you look at the electron, it determines what the state of the electron is. You can do this again with 2 hydrogen atoms, so now you represent 2 bits of information. And again, the system doesn't make up its mind which of these 4 possibilities it's in. So you get a complex number for each of these. Ground, 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 excited, excited, ground, excited, excited. Okay. I won't go through this. You know, there's a rule for measurement for, for 2 qubits, which is the same as 1, but now what happens if you measure only the first qubit, first electron? Well, this tells you what happened, but okay. I won't go through this. The only other thing I want to say is that, this notation, which is called Ket notation, is another way of saying that the state of these 2 electrons is a unit vector in a 4-dimensional complex vector space, right? Because you have 4 complex numbers to describe the state, and they're normalized so that the sum of their squares is 1. Now, the whole potential of quantum computation comes from this observation. So suppose you have n such hydrogen atoms. So think of n as a few hundred, 500. Okay, so now what's the state of these 500 hydrogen atoms? Well, it's a superposition. Again, they don't make up their mind which of the 2 to the 500 bit strings it's in. So it's going to be a superposition of all possible 500 bit strings, 0, 0, 0, 0 through 1, 1, 1, 1, 1. There are 2 to the 500 of them. Another way of saying it is that the state is a unit vector in a 2 to the n dimensional complex Hilbert space. So there's this enormous vector space, and the state is a unit vector in that space. Okay, so now you could sort of say, but this is ridiculous. It's only 500 hydrogen atoms. To describe them, we need 2 to the 500 complex numbers. How does nature keep track of this information? Where is it storing this information? Okay, well, we don't know. But the viewpoint that quantum computation takes is, if you can't beat him, join him. So if you, well, if we can't understand it, let's at least try to exploit it to do computation. Here's the other thing about this, which is, what happens if you now apply some Hamiltonian, you apply some force to a couple of these qubits? How does the state of the system evolve in time? So what happens is really elegant, very beautiful, elegant. What happens is this unit vector that you have in this enormous dimensional complex vector space, 2 to the 500 dimensional complex vector space. So what happens is that when you apply this transformation here on these 2 qubits, when you apply this transformation on these 2 hydrogen atoms, this entire Hilbert space rotates. Okay? And the state moves with this, it just rotates along with the space. And so what happens is all these 2 to the 500 complex numbers have to get updated. So if you want a mental image, it's as though nature had 2 to the 500 pieces of scratch paper on the side, each with a complex number written on it. And then every time you do something to the system, it crosses out these complex numbers and writes new ones in the place. Okay, but now, if you want to think about how big 2 to the 500 is, it's larger than the number of particles in the universe estimated. It's larger than the estimated age of the universe in femtoseconds. It's larger than the product of these 2. And so if you were to think of what's the biggest computation you could possibly hope to carry out classically, well, it's certainly no bigger than 2 to the 500. Right? If every particle in the universe was a computer, and it was a really fast computer, much faster than anything we have today, the age of the universe would not be sufficient to do this many steps, 2 to the 500 steps. Okay, so that's the hope behind quantum computation. There's a bit of a rub. The rub is that when you measure this, this is sort of the private world of nature, this exponential superposition. When you look at the system, it quickly makes up its mind which of the 2 to the 500-bit strings it's in. And you get to see some such string x, like 010101. You see one of these, x, with probability alpha x magnitude squared. Okay. Right. So nature behaves like one of these people, who, you suspect that they're always doing something interesting. But then whenever you talk to them and you say, what's up? They say, nothing. Okay. So the challenge of quantum computation is this, of quantum algorithms is this. How do you get nature to reveal these secrets? How do you, despite nature working so hard to obfuscate, so a lot is happening behind the scenes, but when we look, almost nothing is happening. How do we make something good come out of it? So probably the most famous quantum algorithm has to do with the factoring problem. You're given a number, n, and you want to factorize it into its prime factors. Why do you want to do it? Well, because RSA told us it's important. This is SRA, Shamir, Rivest, and Edelman. Okay. So what they told us is that if factoring numbers is difficult, and it seems to be, then you can use it to do cryptography, to implement a public key crypto system. So when you buy stuff online, this is what you're using. This is how you send your credit card number. Okay. And this scheme is great until you look at Shor's quantum factoring algorithm. So if there's a quantum computer, you can factor in very quickly. You can make use of this work, this exponential amount of work that's going on behind the scenes. Okay, so this is what the course is about. It's this kind of thing. It's about the basics of quantum computation, of algorithms, of quantum complexity. Okay. Okay. There's a second aspect to the course, which is that it does not require any prerequisite in terms of quantum mechanics. So in fact, it starts with an introduction to quantum mechanics. So this might seem a bit funny because it's an 8-week course, and the first part is an introduction to quantum mechanics. The second part is an introduction to quantum computation, quantum algorithms. Well, of course, the first part helps you do the second part as well, but it's still quite remarkable that one can fit all this in. So why is it that one can fit this in? Well, the reason is because instead of studying continuous quantum systems, which are very, mathematically very complicated objects, instead one starts with qubits, which are very simple objects. Okay? And then one starts with quantum gates, which are also simple objects. Okay. Then there's one other thing I decided to do in this course, which is, how many of you know about this Kanban approach? Yeah, well, okay, good. So do you remember many of you don't remember because you weren't around then, but in the early 90s, in about 1990, Japan was supposed to take over the world. They did everything better than everybody else, including manufacturing. So they had this method of doing manufacturing, which is a wonderful thing to know about if somebody, this is a great thing to know about because it comes up as an excellent excuse. So what it says is, this approach says is, you should do things just in time. Don't do them too far in advance because it's inefficient to do so. Well, this was with respect to production. So instead of keeping a lot of inventory, this was a method of keeping lean inventory, so that they coordinated between all their suppliers and made sure that just as things were required in your factory, they appeared magically, and and this really increased their efficiency a lot. It also made sure that they were, they could react to circumstances very quickly. So if something went wrong, they didn't have all this inventory set up, and they could change very quickly. Okay, so what does Kanban have to do with this course? Well, so what I decided to do was a Kanban approach to math. Because okay, so because in this course you have to balance many things, right? On the one hand, quantum mechanics is paradoxical, right? So you're getting the students to understand the basics of quantum mechanics, the basic axioms. You want them to understand what it all means. I mean, it's one thing to sort of say, here are the axioms, now go home. But that's not the way it works. These axioms are, in quantum mechanics, the axioms are particularly simple. Understanding them is particularly hard, right? And so the thought was, if one throws a lot of math at them, then they will not understand what it all means. You want to have very little math. You want to present things as intuitively as possible, so that the students actually understand what's going on. They get a feel for, because quantum mechanics is nothing like what we have experienced. And so, if in addition to that you throw math at them, which they are not prepared to look at, then it's a disaster. So instead, what I did was a Kanban approach to that. So the other thing I did was emphasize the paradoxes, the paradoxical aspects of quantum mechanics. So I'll show you how. And then there was one other aspect which I guess oops, sorry. How many of you know about the Nobel Prize in Physics this year? Right? It went to Harosh and Wineland for AMO physics. Right? It was experimental realization of qubits. And that's what so in a typical quantum mechanics course, in an old quantum mechanics course, quantum mechanics is this theory that describes nature in the small. It's sort of not something that you experiment with at any level of control. I mean, you might do experiments, but they are sort of, you don't really exercise quantum mechanics to any great degree. Whereas these experiments do exercise quantum mechanics to a great, degree of, depth. And so that's what the course has, is a few lectures on how do you actually manipulate and control qubits in the lab. What are the principles behind it? Okay. Let me just say what let me show you what this actually ends up doing. I don't know. Can you read any of this? Is it a disaster? You can. Okay. Okay. So here are the first few lectures, right? So this is already, there are 2 lectures per week. So this is the second lecture. First one is introduction. The second one already talks about qubits and the axioms of quantum mechanics. And okay, so let me say a little bit about the anatomy of a MOOC, right? So you'll see that each lecture has been divided into smaller videos, right? Typically, these are supposed to be 5 to 15 minutes long. Okay. Now, when I first started trying to do this, I thought, this might be okay for a Mickey Mouse course. But if you do something serious, you want to spend an hour and a half on your topic. What is, if you're going to make these short 5-10 minute videos, surely that's not very serious, right? Give me a break. Okay. So, but then I had my lectures videotaped from that spring offering of the course, when I actually taught the course. And I looked at the slides, I looked at the, and I realized that if I were to cluster each of the lectures into its natural components, in fact, I would get videos that were 5 to 10 minutes long, maybe 15. Okay? In fact, what I realized is the fact that they were not already clustered in this way was sheer laziness on my part. That it was much better for the students if it was clustered in that form. Okay? So I felt that making this online course taught me more about teaching than I'd learned in the last decade or two. It was a big deal. There were things that I learned which were, maybe it's just that persistence of vision, right? You do a thing one way and you do it one way, and then you change everything and suddenly you're thinking about it again. It could be that. It could be that these constraints are extremely important constraints. They are very fundamental constraints. I don't know. But certainly I learned more, than I can. Okay, so the other aspect of these videos is during the course of these videos, so the video is, me on a tablet, sort of, so it starts with it starts with about 30 seconds or a minute of video of me speaking, and from then on it just becomes a webcast, a screencast of the tablet. So it's just writing on the tablet. The reason for doing this is that, on the one hand they feel that having the actual instructor show up in some form is very reassuring for the students. It creates a sense of contact. But then after 30 seconds you don't want to carry that video along. It's inefficient. It just doesn't add that much. It's much better just to do. Okay. The other thing that happens with these online courses is that with each of these videos, they're interrupted once or twice during the video, and there's a question that's served up, a simple multiple choice question, to make sure that the person is actually following. Okay? Actually, let me modify that. It doesn't even matter whether the person is following. It's to make sure that the person is engaged, because learning, true learning is active learning. You have to make sure that the person is not just sitting there, daydreaming, that they're actually active. So you could even, as far as I'm concerned, you could even serve up a question saying, is it raining outside? And that would be fine. It just wakes them up and makes sure they're engaged. But of course, if you make up a question which is relevant to what you're talking about, it's even better. Okay. Yeah.
Do you have an audience when you do this, or you just?
No, I did not have an audience. I was just doing it. Yeah, I was just doing it in my office.
I've noticed from my own experience that when I'm listening to the last portion of the video,
Yeah.
I am less engaged.
Yeah.
Because I know there's no question coming
I
up
see.
again except until the quiz.
Yeah.
But I am a little more awake
In the beginning. Oh, I see. Okay, well, that's a good point. We should probably add in a question right at the end as well. Yes. Yeah. Okay, so now let me show you what the first few lectures are. So this is through week 3 of the course, the 3rd week of the course. So the first, the second lecture already, that's week 1. It already talks about qubits, superposition principle, the geometric interpretation, vectors, etc., measurement, and then the uncertainty principle for qubits. Okay, so you can see, right from the get-go, they're seeing interesting concepts in the second lecture already. The 3rd lecture is already talking about 2 qubits, entanglement, the EPR, Einstein-Podolsky-Rosen paradox. Okay. In the 4th lecture, meaning the end of week 2, they already see Bell's experiment. Bell's experiment, which shows that there was no Well, actually, the CHSH form of it. It's very simple, okay? But, they see it. They see that quantum mechanics is inconsistent with any local hidden variable theory. Now, this is quite remarkable, right? Because this is what Einstein spent the last 2 decades of his life trying to do. So if he understood what these students understand in the end of their second week, he could have saved 2 decades of his life. Right? So this is just to give you a sense of, you take this approach towards quantum mechanics, and you can get to very interesting subject matter very quickly. Because it's so much simpler. It's so much simpler to cover this material. Still in the Kanban approach. Yeah, still Kanban. Okay, lecture 5 is quantum gates, no cloning theorem, unitary transforms. Lecture 6 is quantum teleportation. Okay. Now, let me tell you one thing that happened in this lecture, in the 6th lecture. So, at the end of this lecture, I sort of got carried away. And I said, if you want to think about it, some of these topics like the CHSH and teleportation, these are really there's current research that builds upon this, and I described to them in a few minutes what that current research was, and I gave them pointers. And in this class, I was doing surveys, using SurveyMonkey, and it's really remarkable when you do a survey in this class, because you put up the survey and, within within a few hours you have 1,000 responses. It's actually quite remarkable. I've never seen anything like it. And of course, you have to wait 24 hours before you get a good sample, because, if your sample is biased by location, geographical location, you really don't want to go around the world. Okay.
So hold on, what's your audience?
Oh, I'll get to that. I'll give you the statistics of the course in a minute. Yeah. Now, in this survey, what I heard is that there's a real desire for hearing about research topics. So, what I understood is, sure, there are these massive online courses, which try to attract thousands of students, but maybe there's a different kind of audience of a few hundred students or a few hundred researchers. If you have a research viewpoint, so the point is, as you go away from the main centers of research, you still have very smart people around. They just don't know what they should work on. And so every so often we have somebody apply for something, come by, and you say, this guy is so smart. Why is he working on this entirely, this kind of topic which is not motivated, it's complicated, what a waste of time. And so instead you could have these online courses that flatten the research world, right? Where you sort of say, here's a point of view on research. Here are the interesting questions. Here are the interesting papers. That's what I think. This is where you should go. Okay, so here's the anatomy of a MOOC. So it's a 6 to 8 week course. Each week, so in my case, it was an 8-week course. Each week has 2 lectures broken into 5 to 15-minute chunks, 1 to 2 simple multiple choice questions served up during the video. Each week there's an assignment, a homework assignment that's auto-graded. So how do you auto-grade assignments? Well, you either do hashing, so you either use multiple choice or numerical answers. So if the person worked things out correctly, you hope that the only way they can get the right answer is if they got a good model of what they were thinking about. And so, it took some work to figure out how to do all this, to design questions so that they did satisfy this constraint that people who solved these questions were actually understanding concepts. There's one more aspect to this, to making up a MOOC, which is really interesting. When you make up an online video, you make up a lecture, you go into lecture, you sort of give the lecture, it's no big deal, right? Now you're putting up your lecture online. Suddenly, it's not so easy anymore. Because you're thinking, did I get everything right? Is it really, is it really done well? Maybe not, I should, there's this perfectionism that comes into play. Well, luckily or unluckily, in my case, just as I was putting this course online, there was a family medical emergency, so I could hardly put in any time into the course. So all I was doing was I would set up the thing, I'd make up the lecture, I'd ship it off to my grad student who was editing it. That's it. I didn't look back. If it was bad, it was bad. There was nothing to do about it. But this is something that you have to come to terms with if you're going to make up such a course. The other thing you can do online in terms of automatic grading of assignments is if you get them to write code, programs, then there's technology to auto-grade those. Here's a very important aspect of the online course. So this is the reason that these courses are not like textbooks, okay, or recorded lectures. See, learning is very much a social phenomenon. There are some students for whom it's not. You give them a textbook, give them a good textbook, they'll be perfectly happy with it. They'll learn they'll learn better than in a classroom. But for most students, learning is a social phenomenon. And so this is why I think that these previous attempts at doing the learning via textbooks, TV, YouTube lectures doesn't work so well because it's isolated. What do these MOOCs have that those don't? Well, they have an online discussion forum where students can post questions. It's like Piazza. I don't know if you know this online courseware where students can post questions. Anybody can answer them. But then you also get to look at the answers and vote it up or down. And usually, answers that get voted up are correct. But then there's also this more sophisticated version. I don't know how many of you know about Stack Overflow, where you can assign a sort of reputation points to people. And so you have a few TAs who sort of go through and assign reputation points to some people who give particularly good answers, and then the system sort of propagates those constraints, and and the reliability of the system is remarkable. But here's the other thing that it does. What it does is now the learning is truly interactive in a way that in-class learning is not. You see, because, well, I just finished teaching a course at Berkeley. It was one of the largest courses I taught. It had 400 students in class. I did carry on a conversation with the students. There were some students who would ask questions, I'd answer. But still, most students didn't. How can you answer 400 questions? Right? Whereas in this case, once you have so many students taking a course, anybody posts a question, you usually see an answer within minutes. Right? Well, that's quite interactive. That's remarkable interaction. There's also interaction in these assignments. So usually, you hand out assignments, they turn in the homework a week later, and then it's sent to the course grader, who then takes a week or two before they see it back, and then by then they are completely uninterested in what happened. Right? Here, what happens? Well, they do the assignment, and as they are doing the answers, they get to see whether they got it correct or wrong, and they get to take it again if they want. Right? So every attempt, so let's say the first attempt is out of 100%, the second one might be out of 90%, etc. But they get to keep doing the assignment until they figured out what was going on. Also, I didn't have the time for this, but you could also give them partial feedback. So if they gave this wrong answer, you could say, well, probably you misunderstand this concept. Right? Okay. There's a third aspect of this. One thing students do in courses, I don't know if you've encountered this. In my courses, this happens all the time. So students are paying attention, and then at a crucial point, they'll blank out. Their mind will wander. And then, because they blanked out, and if the lecture is not completely fail-safe, if everything's not repeated 3 times, then now they don't follow anything else. But on the other hand, if you repeat everything 3 times, it becomes boring. Right? So what do you do? Well, here, what happens is with this video, they can go back and watch it again. In fact, one of the things that they like to do is watch it in 2x, twice as fast. Because it's boring to watch a lecture in real time, right? So you go 2x, and then when you come to a concept that you're missing, you go back over it a few times, and then, right? So it seems to me it's a little more, custom designed than classroom teaching. Right? Okay. Then there's a final exam, in which there's either an honor code, which is what we did, or it could be supervised, which is the model that they're looking into, where people go into one of these testing centers like GRE, they take the exam there. There are other models where you have online monitoring, where each you have people who monitor the exam online through webcams, and they turn on the sound, the webcam, they take control over the screen, the webcam, the sound. They make sure that the room's fine, nobody's coming in, etc., and they watch. And apparently, people who take the exam this way say that it's more taxing than taking it in class, because when you have one person watching over 100 students, what are they going to see? Yeah, okay, and then there's the certificate of completion, which is a big open question. Is it going to be a real certificate, or is it going to be, just something that says informally you've completed the course? Okay, here are the course statistics. So about 25K signed up, 25,000, maybe 26, 27, I don't know, something like that. I was quite surprised, because I was expecting, a few hundred, 1,000, something like that. But okay, but then it's subject to these factors of 2, right? That I talked about. So the completion rate of any of these courses is about 8 to 10%. So about half of those finished watching the first lecture, about half of those submitted the first homework. 3 to 4K watched the last lecture, about 2K submitted the final exam, almost 2K got the certificate. So the certificate was anybody who scored 80% or higher on the assignments. So the people at Coursera were quite amazed, because they said this was probably the most intensive course that they had seen to date, and they were surprised at the amount of activity in the course, and how on the discussion forums and so on. About 400 got a certificate with distinction, which meant, so for some reason, we had a few extra credit questions, so instead of 100, it was graded out of 103. And distinction was everybody who got over 100. So here are more course statistics. There, 1/3 of the students were from the US. Then there was the BRICS countries, Brazil, India, Russia, without C. China was a non-participant. It was less than 1%.
That is surprising.
Yeah, I don't know why. I think it could have to do with internet access. Maybe the government doesn't want. I'm sure they have no problems with the quantum computing course, but I'm sure there are other courses that they might object to, possibly, or it could be just a language issue. I don't know. I'm sorry. It could be a language issue. We don't know. But if it is an access issue, then this could be a big problem for China.
Japan and Korea are not the right?
Oh well, I've left them off. Okay, so these are the top few. So England, France, Spain, etc. About half the students were in ECS, about 30% physics, some math, then there were various. About 50 to 60% had no prior exposure to quantum mechanics. about 50 to 60% are currently at a university. About 8 to 10% were faculty. Okay. So, I'm sorry?
How many undergrads?
You know, I don't remember. I think that maybe of these 50 to 60%, perhaps it was about 15, 20, 20%, something like that, were undergrads. So it was undergrads, grad students, there were a lot of master's students, and then PhD postdocs. Actually, I was surprised at the number of, my student was visiting a group at a research group in quantum computation in Amsterdam, the CWI. And she said that postdocs were taking the course. And so I said, why are they taking, and then it turned out, okay, so they're doing their physics, they were approaching quantum computing from the physics viewpoint, and this was interesting for them.
Maybe we should ask here, in this audience.
By the way, I would highly recommend SurveyMonkey to people who don't use it already. It's really great. Those are the lectures. There were 16 of them. That's what I already showed you. Then okay. You see Kanban, right? So lecture 7 is where I finally broke down and told them about the bracket notation and Hermitian matrices, tensor products, etc. So before that, in lectures 1 through 6 or 2 through 6, we were doing it all informally. And then finally I sort of said, look, here's what's going on behind the scenes. Okay. There were a few of these lectures where, again, I pointed at current research directions, and again, end of the semester, end of the course, there were a lot of the students. I think about 30–40% said that this is something they wanted to see more of. This was particularly important to them. The students formed study groups, from various parts of the world. So you can see, and some of these study groups were online, some of them were offline. So they used the internet, this forum to coordinate and either meet up physically or on Google Plus or Google Chat, etc. There was a discussion forum, where it was very active. This was towards the end. This is talking about the fact that the course is now moving to edX. So the new version of the course will start February 6th on edX, and my view of it was that this was I thought this was a good course, but I feel that this course could be a great course if it was done right. And if I have time, that's what I want to do on edX this time, to really make it a great course. Here's what an assignment looks like. I'll just show you what. Okay, so there are multiple choice questions which say, well, you're looking at the quantum Fourier transform or them, so you want to know what's omega, so just simple things about what, if you do a quantum Fourier transform or from some periodic superposition, what's the answer? What's the new superposition? What happens if you shift it? So again, they could laboriously go through and do it but if they understand, then this is all very simple. And then there are more complex questions where, okay, sorry, I can't read it, and I don't expect you to, but this is sort of exercising this question, whether they understood this concept of periodic superpositions and what the Fourier transform does to them, and so on. And it's really carrying through an example and seeing that they really understood it, which is the sort of thing you'd want to do. Okay, sorry, it keeps going. And then, every time they check this thing saying in accordance with the honor code, so there was an honor code, and we hope they followed it, but we don't know. Okay, in terms of feedback, so this was on the discussion forum. There was also feedback on SurveyMonkey. I have to say, I've never, in all my years of teaching at Berkeley, Harvard, I've never had as positive feedback in a course. Maybe it's just because it's a free course, I didn't owe them anything, and they were grateful. But it was more than that. There were also there were also people who took it to. There was a professor at UMass who's director of some AI lab, and he wrote to me. He said, well, he took the course. He didn't think he'd get through it. He started it. And then he realized it just carried him along, and it was this is something he had always wanted to do, quantum mechanics, and it was, so. Okay, so let me come back to the question I started with. So what does it, what does this imply for for universities and faculty? So I think that the answer depends upon how good a job you think universities are currently doing. Okay? So, in other words, you think about what it would mean to actually do a perfect job of education, or as close to perfection as possible, a really good job of education. And how close are universities coming today? So are they like almost 100%? Are they 90%? Are they at 50%? Are they at 25%? Okay. So I have an opinion about it. I'm curious to hear what people think. So how many people think it's close to 100%? 90%? 50 to 90%? Oh my God.
If you take world average,
I'm sorry?
if you take average over many universities.
Oh, say a good university. Just take one of the top universities. In India, and anywhere else in the US.
Maybe 60%.
Right. So how many? Let me ask the question again now that it's clear what I mean. So how many people think that top universities are coming close to 100% in terms of achieving educational potential? Nobody, really? I'm sorry.
Can I supplement that? I think that's an intangible, isn't it? Can you put a...
Yeah, no, I know it's an intangible, but sometimes let me ask the question anyway, and then I'll. Yeah. So how about 90%? No? 50%? 50 to 90? How about 25 to 50? And below 25? Okay, so, all right, so it seems most of you who are willing to answer think it's between 50 and 90. Okay, so I think the answer to this question really depends upon the answer to this. So I personally think that they're not doing a great job. I think they're probably in the 25-50% range. Yeah? Maybe even lower. So if we believe this, if we believe that this is what the current state of affairs is, then what's the effect of MOOCs, these massive online courses? Well, first of all, they'll make this level, roughly this level of education, available much more widely. The current level of education at top universities will make that much more widely available. But then it'll also free up faculty time to do a much better job of teaching in-class students. So I think that what will happen is that those who actually go to a university will now get much higher quality education. So it'll just raise everybody. People, everybody will have a basic access to a certain level of education, and then you take this fact that this thing that I was speaking about, that what really matters in education is you really want somebody to look at what you're doing and say, here's your blind spot. You're struggling so hard with all these things, but what's holding you back is not the things you're struggling with, but something else. So why don't you take care of that? And that's what people will pay to go to a university for, because they'll be, they'll talk to real experts who will inspire them, who will also provide them with this feedback. Now, what happens if you think the answer is not this? If you think the answer is 90% or 90%? Okay, so if you think that they're doing almost as well as they can, people will still want to go to the top universities. Why? Because unfortunately, education is not only about knowledge, it's also an arms race. You know, it's a strategic advantage. So if you can go from 80% to 95% by going to a university, there are people who will go to it. So maybe what it'll do is it'll make, you know, it might shrink the number of universities. It may not, actually. You know, so universities might be places where you have access to all these courses, but then you also have somebody who translates these courses for you. You know, takes you from where you are, you know, takes the students from where they are to being able to understand these courses. Okay. I'm sorry?
There will be less job opportunities for teachers.
It could be. You know,
Staff will reduce.
it could be. You know, so let me tell you one way I think about this. So, you know, there's a yoga phenomenon.
Yeah, then we will have to find that.
It could be that it reduces the number of jobs for teachers. You know, it could be that what it does is it takes the, you know, nth tier universities and it says, you know, anything nth tier or greater, you know, those are going to disappear. That might happen. It could be that now it would be possible for a single entrepreneurial, well-qualified person to open a university, you know, where they could say, you know, here's a cottage university, you know, where they are qualified, they got their PhD somewhere, or undergraduate degree from a good university, and they are now in Delhi, and they open a university. Because what this university does is it admits students who now get tutored by this person, or, you know, this person sort of makes sure that they can follow these courses and participate in them at a reasonable level.
Outsourcing the lower level education to someone else. Say you want to join our course, do their online course or something like that.
Yeah.
Outsource it to somebody else.
Yeah.
So the high point remains with the few.
That's right.
The others outsource, you know, customize. Like
Yeah.
SLP, you know, do the SAP customizing.
Right.
So you to customize it.
Definitely, there will be value for many.
Yeah.
Maybe people will get nice presentation.
Okay, so I'm actually through, so I'm, you know, great.
One more thing is, I want to tell you, this yield, you said 25K students
Yes.
signed up for the course,
Yes.
and only 2K students
Finished.
passed, right?
Yeah.
Why the yield is so low?
Well, you know, you could say that the yield is low.
Because the quality of...
Sorry, let me answer the question. So you could either say that the yield is low, or you could say, you know, when I teach this course at Berkeley, each year I teach 35 students. You know, here the number of students who pass was about 50 times greater. So it's as though I did 50 years worth of teaching in one shot. Okay.
No, I just wanted to tell you.
And in terms of let me just clarify. In terms of you know, this is something that's been observed. You know, by now there are many courses that have been taught, and these numbers don't change. Basically, the number who actually finish the course is between 6 and 10%, something like that. And the reason is there's no barrier to entry. You know, so in other words, you're browsing, and you see this course, and you say, oh, maybe I'll sign up. Okay, so you sign up. 1 month later, the course starts. You're nowhere to be seen. Okay, so that's 50% of the people who signed up already. Okay, then there are the people who or not 50%, maybe 25%. Then there are the people who start watching the first lecture, and they don't make it through. So by the time you look at those who didn't make it through the first lecture, it's 50%. Because, you know, it sounded interesting to them, but they don't have the time, and it's not quite what they wanted. So it's, you know, it's perfectly understandable. You know, if somebody tells you, you have an option to take this course if you want, you come browse. If you're going to come browse, well, 50% won't browse. Then there's the question, how many of them would actually do something active like a homework? Well, some of them, you know, were they just didn't want to, they were already, you know, they were postdocs already or something. They were thinking, okay, this is simple for me. I'm just signed up, and it'll get to interesting parts later, and that's what I'll do. Okay, so, but in any case, that's another factor of 2, down to 6,000. And then after that, the number who drop off is not as large, because from the 6,000, there were about 4,000 who were still following the course at the end of the whole session. And of those 4,000, 2,000 attempted the final exam, or 2,500. Yes, that's how it goes.
No, that is that. We are talking about. This is an attitudinal problem. Whatever you said is a attitudinal issue. I'm not talking about it. Supposing there are about 500 students that they taken the same course in a classroom, let's say. What would have been the yield? Out of 500 students, how many would have scored?
Well, in a classroom.
It's a manual system.
I'm sorry, but I don't think it's a relevant question. It's not a relevant question.
No. You're got that.
You know, you could, for example, say we are going to have a test before you start the course, and only if you get over 100, 99% in this test are you allowed to take the course. And then you could say, condition on that, how many of them actually finish the course? Well, you probably get 100%. Okay, but that's not a relevant question. It doesn't matter. It's a different way of doing things. Yeah.
I'm not sure I understood why you said that it would free up, in the previous slide, that it would free up faculty time. Is that because of the availability of teaching materials?
Well, it would free up faculty time in the sense that you could do a reverse lecture. In the sense that, one thing you can do is the lectures are recorded already, and the students watch them on their time. And then they...
You mean for the same faculty who's teaching?
No, for any faculty at all who's teaching the course, who wants to use this material.
Because I don't think the audience would be the same. The audience who's taking the landed class are probably among that 25,000 who signed on but didn't get through the first lecture and things like that. It's probably a large fraction of the classes probably among them.
I'm sorry, I didn't follow what you're saying, so.
Well,
Maybe we can take it up afterwards. Yeah.
Let's take it in order. Ravi next, and then.
Yeah, so I'm taking your course, and well, let me just thank you for a good course. I enrolled especially for the quantum computation part of it, because I'm a physics student, so I already knew. The stats said that there were some 30% physics students.
Yeah.
So firstly, I had a comment to make about a question that was just asked about that the fact that there are 25K students signing up and only 2K eventually finish the course. Well, and the fact that there's no entry barrier, right? And I think that's a good thing that there's no entry barrier, because plus, of course, it's not like you're actually getting a degree from Berkeley for completing this course. So the 2K that actually finished the course did it because they actually wanted to learn something, and
That's
not
right.
particularly because they were looking for some reward other than
That's
the
right.
learning.
That's right. That's right.
So it's a great thing that 2K people did a course without earning a formal degree. They went through. I'm assuming the course was fairly at the same level that it's offered at Berkeley.
Yeah.
Fairly. That's a great thing, right? 2K people finished the course without. They did want to learn something. So this was the first thing. That's why I think there shouldn't be any entry barriers. As for me, I have signed up for some 10 other courses in Coursera. This was the only one I finished because I could find some time for it and some motivation. But the other ones that I'm dabbling in is essentially because I want to really see, is there something interesting there that I really want to learn?
Sure.
And if there is, I will continue with it. Or sometimes I just, leave a course in 3 weeks.
Right.
Still, I've learned something.
Sure.
So I don't think there should be entry barriers at all.
Mm-hmm.
So this is one thing, and the other thing I wanted to ask you. So this is the question part of the question. So the question was, the stats said that a lot of the people who took the course were actually postdocs or faculty, in fact, right? Or PhD students, master's students.
Right.
Some percentage.
Well, you said some 25% were undergrads. Rest of them were either master's students or independent learners.
Right.
Right. So I was just wondering if, considering that stat, if you would contemplate probably offering a graduate course in quantum complexity. Because that is something I I was really searching around the web for some courses, but
Right. Well,
I've never had a course in quantum complexity, so that will be something new for me.
right.
I'm sure for a lot of other people.
So let me say, making up a course like this actually is quite a large investment in time, and you know, it's so I'll definitely consider it, you know, consider doing it, but I don't know how soon, because it definitely takes away time from research. You know, there are various commitments one has, and you know, it's not. I'm sorry?
Did you get paid for it?
No, not at all. Right. It's entirely gratis. Yeah.
Yeah.
So
Yeah.
I have two questions. So
Yeah.
one is concerning offering an online course in, let's say, where writing proofs is intensive, for instance.
Yes.
So how do you?
Yeah.
So how
That's a very good question. Should I answer that? And yeah. Okay. So actually, this is something I'm thinking about actively, because this last semester I was teaching the undergrad course on discrete math for ECS. That's the one in which there were 400 students in class. So, you know, it was, and so I've been thinking about how to put it online, and if I can figure out how to do it, I'll actually. That's the next thing I'll do is do that over the summer or something. You know, the thing about I think that you know, here's one way to think about this whole thing. You know, so I'm sure you've read this you know, thing, the question that Richard Dawkins asks, which is, what good is half an eye? Right? You know, how did the eye evolve? You know, how could it possibly be that you know, half an eye would be completely useless? And it's a little bit like that, in the sense that, you know, when we think about these courses, we think that they are perfect as they are. Actually, you know, if you look at how, well, I don't know, maybe at IIT they are great. Okay, but you know, but you look at well, if I look at how it was, you know, the proofs that are written up in these classes, in the assignments, you have to have a strong stomach to read some of them. And then you look at the, you know, then the grading resources that are available are not that extensive, and so you look at the feedback that they get on these gems of answers, and you say, oh my God, you know, that's what we're doing. So all we need to do is match that or exceed that, and we're already off to the races, right? So that's the thing, you know. So what I'm trying to do is see how to do something, you know, something that's good enough.
So one quickly is about accessibility problems. For instance, people with well, let me put it this way: people who are differently able, as they are called. So, for instance, people might not be able to
visibility.
Yeah. Yeah. So how would they be able to have access to the course? I mean, so different disabilities, you would have to handle them differently. So
right. So this is all handled sort of centrally. So, for example, with Coursera, they had some way of handling it so that you know, the videos were all transcribed. So, you know, so anyone who had trouble either understanding the speech or so on could actually you know, get a transcript of all the videos. So there are certain measures that are already in place, and there are others that are in the works. But that's handled sort of centrally. You know, the ideal you know, the ideal way all this would be is that you know, if you want to put up a course online, all you have to think about is the content and giving the lectures. So right now, you know, it took a long time to actually get up to speed and figure out how to do everything. Ideally, these things will you know, evolve.
I think the MOOCs have the ability to transform the university system in a different way, which is to divorce the teaching from the certification. That you might have, at some point, some major US university might decide to give a degree based on online education, and then it's not at all clear whether the teaching given by other universities would be relevant, or would they definitely be challenged in a completely different way. I just want to see what you speculate on that.
Right. May I add one more thing to what you said? So right now, universities are, are really guilty of bundling. The only way you can access a university is if you sign up for 4 years, right? If you want to learn, if you want to learn a smaller subset, that's it's too bad, right? So what this would do is it would unbundle education, right? So in other words, you don't have to subscribe to all the channels with stuff that you don't want. You can subscribe to only the one that, maybe only to the cricket channel or whatever it is.
I think we've had a very long session, so I'm going to call a close right now. Let's thank Umesh for that.